Guys, welcome to lesson 3.7. Today we're going to talk about these things called removable discontinuities. So we've talked about discontinuities quite a bit in the past couple lessons. A discontinuity is when you have some kind of a break in the line, right? We're going to talk about a special group of discontinuities called removable discontinuities. And basically what that means is it's a discontinuity where the limit exists even though the function is not continuous at that point. Okay. Now there's strategies algebraically that we're going to use to find these limits, and one of those things that we're going to talk about is using a method known as factoring. You guys know what factoring is, right? But you could actually use factoring to find the limit of a function that has a removable discontinuity, and I'll show you how to do that. Next, we will also look at what do removable discontinuities look like on graphs. Okay, so all that being said, let's go ahead and jump into a question here. So on the left here, I have the function, we'll call it y1, and it equals x plus 1, and I've got its graph underneath of it. And then on the right here, we have another function, we'll call it y2, and it's got a graph of its function underneath of it. And as you guys can compare these two graphs, even though the equations look extremely different, those two graphs are almost identical with the exception of the fact that the one on the right has a hole in it. Okay? Now, if I were to ask you guys, what is y1 of 1? So y1 means I'm looking at this function. Of 1 means I'm plugging 1 in for x. So if I were to plug 1 in for x, what would I get? Well, I would get 2. And you can see that on your graph here because it has the point 1, 2 right there. What if I asked you guys to find y2 of 1? In other words, we want to plug 1 into the y2 function. Well, if you plug 1 into the top, you're going to get 0. If you plug 1 into the bottom, you also get 0. And you're not allowed to have zeros in the denominator, which means that it doesn't exist. And that is why at this point here we have a hole where x equals 1. Okay, so that's what is essentially making these functions different. But for every other point, they're literally the same. So for instance, if you were to plug in -2 for x, you would get a y value of -1. Same thing over here because they're exactly the same. They have the same input and output for every spot except for that one place there where x equals 1, in which case this one just doesn't exist, but this one equals 2. But let's think about it not in terms of what the function value is, but let's think about it in terms of what the function's approaching. In other words, let's think about it in terms of limits. So, what is the limit of this function as x approaches 1? Well, here's where x equals 1, and if I were to approach it from the left, and if I were to approach it from the right, they both land at the same spot, which is a y value of 2. If I were to try to find the limit of this function over here, function y2, as x approaches 1, as I approach from the left, I'm getting closer and closer to that open dot, and as I approach from the right, I'm getting closer and closer to the same open dot. And as you guys know from previous lessons, the fact that the dot doesn't exist doesn't matter. The question is what y value are we approaching? And we're still approaching the same y value as on the other graph, and that's 2. So here's what I want you guys to notice. They both equal 2, and therefore the limit of function y1 is equal to the limit of the function of y2. And the reason for that is because those two graphs, as you guys can tell, are exactly the same. The only difference is that the one on the right has a hole. Okay? Now, why is this important? Well, so far, the only way that we've learned to find limits for equations is with direct substitution. So let's just say if I gave you guys this problem here, but no graph. Let's say the graph didn't exist and you didn't know what that graph was. And I said, okay guys, help me to find the limit as x approaches 1 of this function here. Well, the only way we've learned how to find limits so far is with direct substitution. So if you did direct substitution, you're going to end up with 0 over 0. And you might mistakenly think, oh, okay, well, therefore it's undefined. It doesn't exist. Okay, well, what I want you guys to remember is that direct substitution is a way to evaluate the limit if the function is continuous. Okay, so if a function is continuous, then direct substitution is the way to go. You just plug in your value for x, and the y you get is the answer. So if I tried to find the limit of this, all I have to do is plug in 1, I've got my answer. But over here, since this function is not continuous at the value x equals 1, we can't really use direct substitution to find the limit. But we just realized something. We realized that, okay, well, I don't know how to find this limit because direct substitution doesn't work. But I do know that this function has the same limit as this function at that point, because those two graphs are exactly the same in every way. The only difference is that this one here doesn't have a hole, but when it comes to holes, it doesn't matter when you're trying to find the limit because you get the same answer anyway. So if somehow we could change this equation here into this equation, then we can use direct substitution to get the answer. And that's what a removable discontinuity is, you guys. A removable discontinuity is where you have a function that has a discontinuity. So you can't do direct substitution because you'll just get undefined. But if there's a way that you can change this equation into this equation, well, now that function's continuous. I've removed the discontinuity. These two functions are exactly the same. It's just that this one over here is the same function as this one without the discontinuity. And so now I can do direct substitution. Okay? So the question now becomes, how do we remove the discontinuity? How do I change this equation into this equation? Because we're not going to have the convenience of being able to look at a graph. So how do we remove the discontinuity? And I'm going to rephrase that as, how can I change that function into this function? Since I know that they're exactly the same function anyway, and the only difference is that hole, but when it comes to holes, limits don't exist. I'm sorry, when it comes to holes, limits do exist anyway, so it doesn't matter if that hole's there. So how can I remove the discontinuity? Or how can I change this function into this? And the strategy I've told you that we're going to be using today, you guys, is the strategy of factoring. I want to show you something here. The top is a difference of squares. The top can be factored. If I factor that, x squared minus 1 is x plus 1 times x minus 1. So I just factored the top. Now I want to show you guys something. When you have something on the top and bottom, they're exactly the same. Those cancel, and look what I'm left with. I'm left with that. Which is that? Okay? So let's review really quick, and then we'll get started. This is what's called a removable discontinuity because the limit actually exists even though the function doesn't. It's a removable discontinuity. I can actually ignore the discontinuity. The trick is you need to find a way to somehow change this equation so it becomes another equation that doesn't have that discontinuity. And once you do that, you can just do direct substitution to find the actual value. And now the question is, how do we change it? And the answer is factoring. So let's go ahead and jump in and do a couple of problems to bring this thing to life for us. So before we jump into some examples, I'll just kind of go over this summary, not stuff that I've already talked about, but it's in your notes, so want to make sure that it's clear. So if you need to make any adjustments, you can. So removable discontinuities, what are they? If you can somehow change a function with a discontinuity so that you get a new function that has the same limit without that discontinuity, then we would call that a removable discontinuity. Now, removable discontinuities are places where the limit exists, but either the function doesn't exist or the function is not equal to the limit. Now, on a graph, what does that interpret as? On a graph, if the function doesn't exist even though the limit does, that looks like a hole. Or you could have a hole with a dot above or below it, in which case, even though the function does exist, which is this black dot, it's not the same thing as the limit, which is the open dot. So these are what discontinuities, removable discontinuities look like on a graph. So what that means is that if you guys see a discontinuity that's a jump like this, that is not a removable discontinuity. In other words, there's nothing you could do to find the limit because the limit literally doesn't exist. Same thing with vertical asymptotes. Those are non-removable discontinuities because you can't, the limit just doesn't exist. And since a removable discontinuity is one where the limit exists, then these are ones that are not removable discontinuities. So if you didn't, I would encourage you guys to add these pictures right here to your notes. It will help with what we're going to do a little bit later on today, actually. Why do we care? Functions that have a discontinuity at a point cannot have the limit determined using direct substitution. So this process that we go through of removing the discontinuity helps us to find the limit of such functions because we can't do just direct substitution. But the question is, how do we do it? Well, hopefully you guys know one of those ways is factoring, but there's actually 4 ways, and we're going to look at all 4 of them. Not today, but we'll look at one of them today and the other ones later. So one way is by factoring and dividing. That's the one we're talking about today. The next one is rationalizing, and another one after that is simplifying complex fractions. Both of those will be next class. And then this one here is the most awesome one of all. It's called L'Hopital's rule, and we'll learn that in a few classes from now. And the reason why L'Hopital's rule is so cool is because it literally works for almost every type of limit you need to find. So even though I'm going to teach you these other 3 limits, L'Hopital will literally do the same job that these ones do, and it's just one quick and easy strategy. So you might wonder, why are we learning the other 3? Well, because I've seen questions asked where they make it so that you have to go using these strategies. So you still want to be familiar with them. But L'Hopital's rule really is the best one, and we'll get to that a little bit later. So for now, let's go ahead and continue our chat here. Let's go ahead and do an actual example problem now. So for all of these problems are functions where I'm asking you to find the limit at a certain value of x. And for all of these problems, if you were to try direct substitution, you're going to end up with no solution because direct substitution is not going to work. So what we're going to have to do is we're going to have to do we're going to have to remove the discontinuity. And the strategy we're practicing today is factoring. Okay, so let's go ahead and get started. So first of all, you don't have to necessarily write this in your notes, although for maybe at least the first problem it might be helpful, is let's try direct substitution just for the heck of it. Because technically, that's usually what you're always going to do first, is you're always just going to try some direct substitution. So if I were to try direct substitution right now, I would end up with the following. Matter of fact, I'm not going to put an equal sign, and I'll talk about why in a second. But direct substitution is where you'll plug in a -1 for x. and then we're going to simplify it. So I have 1 minus 5, which is negative 4, plus 4. Negative 5 plus 4 is negative 4 plus 4 is 0. Now on the bottom we have negative 1 squared, which is 1, plus a negative 1, which is also 0, and it doesn't exist. It's undefined. So now that doesn't mean the limit doesn't exist, though. It might, but it doesn't have to. Okay? All this means is that the function doesn't exist at that point. And if the function doesn't exist at that point, then we can't use direct substitution to find that limit. So I'm not going to say it does not exist, but I will say that direct substitution fails. So we need to try to remove the discontinuity. Okay. Now, you don't need to do this on any of the problems after this because I'm just going to tell you in advance right now that every problem will turn out the same, where if you try direct substitution, it's going to fail. And then after that, we're going to do the same thing for every problem, which is we're going to remove the discontinuity. So you don't need to write this out for every problem. It's kind of pointless. But just for the sake of formality, I just want to show you direct substitution fails, so that cannot tell us what the limit is. So we need to use another strategy, and here's the other strategy. First of all, oh, and by the way, let me bring that back really quick. Remember how I told you I wasn't going to put an equal sign here? And the reason you're not going to put an equal sign is because this is not a number. This is nonsense. You can't have 0 in the denominator. So you can't say that the limit equals nonsense. You can say that the limit doesn't exist, but you can't say that it equals nothingness. So that's weird. So actually, and the reason I'm pointing that out to you is because at one point in the year, at one point in my talk with the College Board about things, they've actually said they've not given students points for writing this, which is, in my opinion, really stupid. But so just so you guys know, if you ever get 0 over 0 as an answer, you never put equals, okay? And we're actually going to see that again when we get to L'Hopital's method. But for now, we'll just leave it at that. But that was a side note. All right, so once again, let's recap here. We tried direct substitution and it failed, so what do we do? All right, so what we're going to do now is now I am going to put an equal sign, and I'm going to keep the limit here. But what I'm going to do is I'm going to factor these expressions. So notice how this one has 3 terms. This is we're going to factor that using trinomial factoring methods. Now, so I'm going to write a little note here for you guys. The answer, what you want to do is you want to factor. And so you're going to get a little bit of factoring review here if you're a little bit weak with factoring, so you might want to pay close attention, take some good notes. If you are weak with factoring, you might want to email me and say, hey Bailey, can you give me some practice problems with factoring, because I really need to get that down, because this is going to be something that continually comes up through the year. You're going to need to know how to factor, okay? So anyway, here we go. So I need to factor. It's going to come out to be 2 things. When you have a trinomial like that, you're going to have 2 binomial factors. And the way that you find these is, first of all, I want to find the first term in each set, and you find that by just asking what times itself, or what times what makes x squared. And the answer is x times x. So you put 1x there, 1x there. And then you ask yourself, what times what makes 4? Now, some of you guys might say 2 and 2. But that's not going to work. The answer is 1 and 4. Okay? And you also have to look at your signs. Now, how do you know which one works? Well, what you do is you just FOIL it out to see if it works. So you do first numbers multiplied together, outer numbers multiplied together, inner numbers multiplied together, and the last numbers multiplied together. And when you're all done, if you combine those 2 in the middle together, you should get this. If you don't, you did something wrong. And that's how I knew that this wasn't going to be 2 and 2, because I just kind of quickly did some mental math. If both of those were 2, I would not have ended up with the correct middle number after foiling it out. So that's a quick little review for you on factoring trinomials. But so if you factor that, you end up with x plus 4 and x plus 1. All right. Next, we need to factor the bottom. Now, this is not a trinomial. That's a binomial. Now, there's 2 different strategies for the binomials. Sometimes you just need to take out a greatest common factor, and sometimes it's what's called a difference of squares. This one is a greatest common factor, and the way you can tell is by looking at this. What do those have in common? If they have something in common that you could divide out, then it's a GCF problem. So what can we divide out of those two numbers? Well, they both have at least one x, right? So I could take an x out of both of those. If you divide this by x, you're left with 1x, and if you divide this by x, you're left with 1. And that's what we call the GCF method. Okay? So now, if you're head spinning with all this factoring, you are somebody who should email me and say, hey Bailey, I need some factoring practice worksheets. Okay? But if you're looking at this and you're like, oh, yeah, I wouldn't have done that at first, but I totally remember that now and I'll get it now, then you're fine. Okay? But you need to know who you are. All right. So let's review. Let's recap. First thing we did was we tried direct substitution and it failed. You don't have to do that for the rest of the day. The next thing we do is, okay, so since that failed, we're going to try to remove the discontinuity, and we're going to do that by factoring, which I just reviewed with you guys here. Now, these two expressions literally are equal to each other because this is literally equal to this, and this is literally equal to this. So it's okay to say that these things are equal to each other. All right, now what? Now we're going to remove the discontinuity. Now, what does that mean? Well, remember how I wasn't allowed to plug in a -1? Well, when you write it like this, it's a little bit easier to see why. If you plug a -1 in here, that's where the 0 comes from, right? -1 plus 1 is 0. So that factor right there is what's causing us to have a discontinuity. It's causing us to get a 0 in the denominator, and we don't want that. Okay? But here's the thing. Notice how it's the same thing on the top and on the bottom? We can divide it out. So we remove the discontinuity by dividing it out. And now I'm left with this. And I am going to put an equal sign because it literally is the same thing, because that's a legal math move. So now I have this. All right. Well, now that I've removed the discontinuity, I'm okay to do direct substitution. Okay, so now I can plug in my -1. So if I do that, let's see what we get. If you plug in -1 to the top and the bottom, you get this. So let's make another note there. That's direct substitution now. Just plugging the number in, which gives me 3 over -1, which is -3, and there's my limit. So this function, as x approaches -1, even though it doesn't exist at -1, it does approach a limit of -3 at that value. So this is a graph where you would have a hole at -1, comma -3, but it would be a hole where the limit exists because it approaches it on both sides. Okay, so let's review. Okay, so when you're doing limits, you try direct substitution first. But if it fails, we're going to do a couple of things. First of all, we're going to try factoring. We're going to factor. After that, we're going to divide out the common factor, or we're going to cancel out whatever's the same on the top and bottom. And after we do that, we try direct substitution again. And at that point, you should get an answer. Okay? And just so you guys know, like I said, we're not going to do this first step anymore because it's always going to turn out the same. Direct substitution is going to fail. So we're just going to start off with step 2 right away and for the rest of the day. Okay? Now, a question might be brewing in some of your guys' mind. What if after you cancel it out, direct substitution still fails? Well, if that didn't work, there may be another method to try to remove the discontinuity, but for the most part, that usually just means it's a non-removable discontinuity. In other words, you can't find the limit at that point. The limit doesn't exist. But I don't think we'll be looking at any problems like that today, so don't worry about it. Okay, so step 1, try direct substitution, but it's not going to work. I've already told you that. So let's jump straight into step 2. Step 2 is to factor. Okay, now I'm going to start with the bottom on this one. This is what we call a difference of squares. We have two perfect squares. The square root of x squared is x, and the square root of 25 is 5, and a subtraction. When you have two perfect squares being subtracted, what you do is you take the square root of this number, or you can say what number multiplies by itself to make that number, which is x, and then you take the square root of this number, or once again, you can ask yourself what number times itself makes 25, and you're going to make one of them positive and one of them negative. That's just a shortcut for the difference of squares method. All right. Now, for the top here, you may notice that 5 minus x looks a little bit like x minus 5, but those are actually different. Okay. So, what are we going to do with that? Well, let's see. For these ones, we're going to factor out a negative 1 when it's backwards like that. Let's factor out a negative 1, which means you're going to divide both of these by negative 1. So if you divide 5 by a negative 1, you're going to get negative 5. And if you divide negative x by negative 1, you're going to get a positive x. And by making the signs opposite and therefore flipping the numbers around, it makes it look like the one on the bottom. So you can just cross these off now. So that's step 2, is to cancel, right? So now I have the limit as x approaches 5 of negative 1 over x plus 5. And then the last step is direct substitution. So if I do direct substitution, I end up with negative 1 over 5 plus 5, which is negative 1/10 is my final answer. So this function would be approaching a y value of negative 1/10 as x approaches 5, even though it doesn't actually exist at x equals 5, because if you plugged it in, you would get a 0 over 0 again. All right. So what I really want you guys to make sure you know for certain here are two things. The steps: factor, cancel, direct sub. Okay, so make sure you know those steps well. The secondary thing that I want you guys to make sure that you know how to do really well is how to factor. We talked about how to factor trinomials. We talked about how to take out GCFs. We talked about how to factor differences of squares. And we also talked about these problems where the numbers are backwards. So if you want to flip them around, you can just factor out a negative 1. But just so you guys know, that only applies to minuses. So for instance, if you had this, you could just flip that around. There's nothing wrong with that. As you guys can see, I've got a positive x and a positive 5. So when I flip it around, it's still the same, right? But if you have this, flipping it around is not the same because it went from being a negative x to a positive x, from a positive 5 to a negative 5. So for this one, you have to factor out a negative 1 to be able to flip it around, but for positives, you don't. Okay? So two things I want you to know. What are the steps? And also reviewing some factoring strategies. So I'm going to let you guys practice this basic strategy at this point, and we'll see how you do. So here are 3 problems I'd like you guys to try. So tell you what I'll do. I'm going to go ahead and we're going to treat number 1 like a guided practice, and then I'm going to let you guys do numbers 2 and 3 on your own. So completely on your own. So let's go ahead and do number 1 together first. So I want you guys to do the first step. Now, by the first step, I don't mean direct substitution, even though technically that's what you're supposed to do, because we already know what's going to happen. It's not going to work. So by the first step, I mean really, what do you do after direct substitution and it fails? Do that step. Okay, pause the video here and write down that first step, and when you're done, you can check your answer. All right, so here it is. So if you didn't get this or you're struggling, once again, you're someone who should probably email me and say, hey, Bailey, I need to practice factoring a little bit. Can you help me out? All right, but anyway, by the way, you know how sometimes you have to pick numbers, like how did I know it was 2 and 3 and not 1 and 6? Well, guys, just so you know, obviously it has to match one of the things on the top, right? If it doesn't match, then nothing's going to cancel. They're not going to give you, I'm not going to give any problems where you won't have something cancel today. So you can kind of cheat and know at least what one of the numbers are supposed to be on the top. So if you know that one of them has to be 2, then the other one has to be 3 so that you get 6. All right. But anyway, all right, so that's step 1. Step 1 was to factor. Let's move on, or actually step 2, right? So let's move on to the next step after that. Pause the video here and write the next step. All right, so there's your next step. Now, guys, I want you to understand that I've emphasized twice now the importance of how you should be showing your work, and I'm going to emphasize it again here. Did you just do this? Did you just put this limit here? Did you just put that equals negative 1 over x minus 3? Because if you did, you're wrong. The limit of this expression does not equal this. The limit of this expression equals the limit of this expression. So you actually have to leave that word limit in the front. If you don't do that, you've actually written something that's incorrect. Because the limit doesn't equal this function, but the limit does equal this limit. So you have to make sure that you're showing your work in the way that I'm showing you, because they're, believe it or not, sometimes those College Board people are really picky about how you show your work. And whenever I tell you, those are the times when they're picky. So make sure you make notes about those so you don't make those mistakes. All right, so anyway, the first thing we did was we factored. The next thing we did after that was we canceled out what they had in common, which left us with what we have there. All right, so go ahead and pause the video here and do the last step. Okay, so the answer is 1. The thing you were supposed to do is direct substitution. You were supposed to just plug the 2 in now. Now, some of you guys might be thinking, Mr. Bailey, you hypocrite, right? You just got through saying up here that you have to write the limit, right? But you didn't do it here. Well, guess what, you guys? After you take the limit, after you do direct substitution, you did the limit. And so now the limit's gone. Now, you guys didn't have to show this work if you didn't want to, because at this point, it's okay to assume that you guys can handle this level of mental math of plugging in a 2. So you don't have to show that many steps. But no, after you plug in the 2, you no longer need the word limit anymore. Okay? So there we have it. Hopefully you guys got that one. Now what we're going to do is we're going to have you guys do a student practice, which means you're going to completely do the other 2 on your own here. So go ahead and pause the video and try to do these 2 problems and see how you do. Okay? Okay, so here are the solutions, and this is a pretty clear way to show your work here. Step 1, factor. Step 2, remove the discontinuity. Step 3, direct substitution. And after you do direct substitution, you no longer write the word limit. Same thing here. Factor, remove, direct sub. So you end up with the answers of -1 and you end up with 1/4. So for both of these functions here at the top, even though the functions do not exist at x equals 1 for this one and at x equals 2 for this one, even though they don't exist, the limit does exist. And so both of these functions would basically have a hole at that point. So for this one, it's as x is approaching an x value of 1, we're approaching a y value of -1. And for this one, as x approaches 2, we're approaching a y value of 1/4. And it's at that open hole dot there. Okay? So direct substitution doesn't work, so we remove the discontinuity and then we try direct substitution again. Since direct substitution fails the first time, that means the function doesn't exist there. But after we remove the discontinuity, if the limit exists then we can assume it's a hole. So the limit actually does exist. All right, so let's go ahead and move on to our last topic here. So now that we've talked about what removable discontinuities are, you should be able to identify them on a graph. Now, we have a lot of discontinuities on this graph, and we want to be able to identify which ones are removable and which ones are not removable. So, for instance, let's go through first and let's find all the discontinuities. So, we have a discontinuity here at x equals -3, right? Because we have a hole right there. We have another discontinuity right here at x equals 0 because there's a jump. We have another discontinuity here at x equals 2, and it's a hole with a dot below it. And we have another discontinuity here at x equals 6 because we have a vertical asymptote. Now remember, removable discontinuities are those discontinuities where the limit actually does exist. Okay? The limit exists if the limit from the left and the limit from the right are both meeting at a common y value, and in this case they are. So this is removable. So x equals -3 is a removable discontinuity. At x equals 0, though, the limit from the left is 0, while the limit from the right is 3. When the limits from the left and right are not the same, that means the limit does not exist. And if the limit does not exist, that's a non-removable discontinuity. In other words, let's just say that I can find another equation that will look exactly like this one, but have no hole there. And therefore, I can use factoring or something to remove the discontinuity and find the limit. But in this case, there's nothing you could do. There's no equation you can ever find that will make us find a limit there. That's impossible. All right, let's take a look at number 2. The limit from the left and the limit from the right are both meeting at a common point. So once again, this one here is a removable discontinuity. And on the left here, even though the limit from the left and the right are both approaching negative infinity, even though the limit, we would say that the limit is negative infinity, remember, infinities means the limit doesn't exist. So in this case, since the limit doesn't exist because it's an infinity, this is a non-removable discontinuity. So that's an example of a discontinuity you can't remove. Now, not that you guys need to know this for this particular set, but for instance, here's an example of a non-removable discontinuity when you look at an equation. Let's say I gave you guys this. Now you guys agree that if I were to plug in 1, I would get 0 on the bottom, and that's undefined, right? So direct substitution fails. So what do? Well, I know. Let's go ahead and factor it and cancel out stuff. But you can't factor anything. There's nothing you can do to this expression to change it. And since I can't change it, you know what that means? There's no way to remove it. And since there's no way to remove it, you know what that means? That means this is a non-removable discontinuity, which means that if you were to graph this, it's either going to look like a jump or a vertical asymptote. Now, you may remember from pre-calculus which it is. It's a vertical asymptote. The only way you could ever get a jump, you guys, is with absolute value functions or with piecewise functions. That's the only way you're ever going to get a jump. But any other kind of function, if you have a discontinuity, it's a non-removable discontinuity. It's probably an asymptote of some kind. Anyway, there's that. So I want you guys to go through here, and I want you guys to identify all the discontinuities and also identify which ones are removable and which ones are not. All right? Pause the video, and when you unpause it, you'll see the solution. Okay, and here's your solutions. X equals -2 is a non-removable discontinuity because the limit doesn't exist. It's a jump discontinuity. X equals 0, there's a vertical asymptote on the y-axis there. At x equals 0, vertical asymptotes are non-removable discontinuities. The limit does not exist. X equals 2, that's a hole. Holes, the limits exist, and that would be a removable discontinuity. And the other one there, it's very tiny, but you guys can tell that's a jump, right? We're going from the solid dot to the open dot at a jump there. And as we already discussed, jumps are non-removable. The limit from the left and right are different. So there you have it. That's the answer, and that's where we'll close out that lesson for the day.